The answer. All right, what did you get? 0.0160. X equals 0.0163. 63. So we're allowed 3 sig figs, it looks like. Yeah, at least 3. So give me one extra digit. 1634. Did you double check it?
Yeah, I did the percent check and the percent was 3.265.
Oh, what did you do?
I can do the assumption at the first reset where.
Okay. You did a reset followed by
the simplifying assumption.
Followed by the simplifying assumption. Okay. Good. And you got a 3.4%.
Yeah.
Okay, then that works. Well, anyway, why don't you guys try to figure this out at home? You want to do that, or do you want to work through it? Work through it.
Yeah, see what we get.
All right. Well, did anybody try to reset? I mean, not reset. Did anybody try the simplifying assumption off these? If you do the simplifying assumption saying it's very close, right? Very close to equilibrium, maybe the change is small. And so let's go ahead and do the simplifying assumption here. That is 0.03,000 plus 2x is about equal to 0.03,000. And then 0.03,000 plus 2x is about equal to 0.03,000, and 0.5,000 minus 2x is about equal to 0.5,000, and 0.5,000 minus x is about equal to 0.5,000. And then try to solve for x. If you try to solve for x, it's funny because there is no x to solve. So will the simplifying assumption work? No. The other method you have is, if you want to go straight off this, you could do the method of successive approximations, where you guess an x. And the x has to be between, what, 0 and 0.2500. Yeah. So between 0 and 0.2500, you could take a guess and then try it. Hopefully, you'll converge on the answer. You could do that. It'll take some time, but you know, in 12 minutes, you probably could have done it. 15 minutes, maybe longer. 20 minutes, 30 minutes. If it's 30 minutes, then you've eaten into half your exam time on one problem. This is, these are strategies you think about on timed exams. Like at UCLA, the exams are 50 minutes long, and so like 12 minutes is actually kind of a big chunk of time to devote to. Depends on how many problems there are, And so if you go on 20 minutes on one problem, 30 minutes on one problem, you're losing a lot of points on others. And so it's one of those things to think about. And so this is why we want as many ways of solving this. And we might not get the perfect answer, but it'll be quick, right? And you'll get an answer versus, you might get a better answer, but take a long time. You get a better answer, take a long time, then you're losing points, maybe. And so just strategies. On our exams, normally, like for example, if I give just a few midterms, I'll give the full lab period for that. Extend it, but depends. It depends if some people might not think it's fair if I extend the time, so we'll see. Well, anyway, what do you think? This looks like a lot of binomials. A lot of multiplying out and squaring binomials. Is that fun? No. So how can I get fewer binomials? Reset. So, I wouldn't even bother with this. There. We should have reset this. Anyway. And reset, we're going to reset it to the left or to the right? I'm going to reset it to the left because this equilibrium should favor the reactants. So let's go ahead and do that. And so we're going to get plus 2y plus y minus 2y minus 2y. And so we look at what is the limiting reactant here? There's none. This is stoichiometric. So both of these are going to go to 0. So this should be 0 molar, 0 molar. And then plus 2y is 0.03,000. So this is going to go to 0.5300. And this will go, what's half of 3,000? 1,500. So this will go 0.5150. 0 molar. And so this would be my reset initial conditions, like this. Okay. And then now we let it go. Remember, this is just shifting all the water to the left. We're just shifting all the atoms to the left. As long as we don't lose any atoms, we're okay, because everything should equilibrate to the same equilibrium. You know, it doesn't matter. It doesn't matter if you have 100 gallons of water in a fixed tub. You know, it doesn't matter if you push all to one side or all to the other. It's going to reach the same equilibrium point. And so the change here is going to be, now it's got to go to the right, minus 2x minus x plus 2x plus 2x. And so at equilibrium, we would change. And so at equilibrium, I expect 0.5300 minus 2x molar, 0.5150 minus x molar, 2x molar, and 2x molar. So now we can plug it in here. We're going to get 2x squared divided by 0.5300 minus 2x squared and 0.5150 minus x for the first. If you look at this equation, this is still a fourth order equation. Can you do that with the Casio, your $20, you know? No, you can't. And so here we still have to use the method of successive approximations, right? At least there's fewer binomials to multiply out, right? Or we could try something else. We could try to use the simplifying assumption, or SA. These SAs aren't the same. This is successive approximations. This is a simplifying assumption. The simplifying assumption, we're going to assume that the change is small. Now, which one is a bigger percent change? 2x from 5,300 or x from 5,150? Which one would result in a bigger percent change? 2x from 5,300. And so the simplifying assumption, if 2x is much, much smaller than 0.5300, then of course x must be smaller than 5,150, right? Because it's half the change. And so we only have to define it for this, and it should hold for both. And so if we apply the simplifying assumption, the SA here, then we get, we'll just go ahead, 2 squared is 4, 16, so we get 16x to the 4th over 0.5300 minus 2x should be about 0.5300, so this is going to be 0.5300 squared. 0.5150 minus x is just going to be 0.5150. Now look, can you do this on your $8 calculator? Yes. And is it going to take much time? No, but we got to hope that it works, because if it fails, if this fails, then we have to use the method of successive approximation. And so let's see if it works. The method of successive approximation is not difficult, and in fact I was supposed to do a problem with, did I do a problem with method of successive approximations? Yes? This semester? No? Okay, I'll talk about it briefly, but somebody tell me what x is? 0.01695. 0.01695. Okay, we're allowed 3 sig figs, so we'll carry one extra. And now I have to determine the percent change to justify it. And so I want the bigger percent change, because if the bigger percent change is still smaller than 5%, then the smaller percent change will definitely be smaller than 5%. And so which one is the bigger percent change? The bigger percent change is going to be 2x over 5,300. The smaller percent change would be x over 5,150. And so we'll do that, 2x over 5,300 times 100%. And what does the percent change come out to? 6.78. 6.78%. So close. So if we did the smaller percent change, let's do the smaller percent change. The smaller percent change would have been x over 5,150. X over 5,150 times 100% is 5.23. So this is, this answer, let's say, because we're always thinking about time on tests. And so, you have different options. If you're running out of time, you could say that, it's going to be close, x is going to be close to this, and you can calculate concentrations that are close, but it's going to be slightly in error because it's exceeding our limit. We're starting to get further and further away, right, from where it works. And so if you're running out of time, some kind of answer, even though it's in slight error, is better than no answer. And so as far as partial credit goes, a person who gets this, but you got to recognize that this is not valid. And this one we wouldn't even calculate it. But this is not valid, but it's close. But we have time. Actually, I don't know how much time we have. We have time. We could figure this out. Let's do this. Let's figure this out. Let's see how long it takes us to figure out. It's not valid, and therefore I need to do what? This. Right? Therefore I need to do that. But, was this a waste of time? This was not a waste of time, because you know what? We have a good first guess. This is not right, but this is pretty close, right? And so let's see where we're at with this first guess. And so let's do the method of successive approximations. Where can I find information about this? This is Appendix A in your book. Appendix A in your book. And so the way I usually set it up is I just do minor simplification. I don't do major simplification. So I just go 16x to the 4th, 0.5300 minus 2x squared, 0.5150 minus x to the first. This should equal 9.14 times 10 to the minus 6. And so what we do is we guess. We guess x is equal to, if we guess x is equal to 0.01695, it's a little much. Let's just go 0.017, because the fewer digits we have, the less calculation we have to do, right? And so let's just go ahead and guess x is equal to 0.017, and then calculate 0.017 to the 4th times 16 divided by parentheses 0.53 minus 0.017, times 2, whatever, and punch it out, and then see what k is equal to. And so if x is equal to this, k equals what? We know this is off anyway, so this is why I rounded it to 0.017, so I have less keys to key into the calculator. Here. Five point 2.3? 1.09, 5.2 times 10 to the negative 6. What is it, 1 or 5? 5? 1? All right. Whichever. It's too. Is it too big or too small? Too small. We have fourth order on top, third order on the bottom. We got to make this bigger, right? And so let's go ahead and make it bigger. I don't know how much it's going to impact. Let's just go 0.018 and see what happens. If we go 0.018, you know, we add sig figs progressively, you know. So let's just try 0.018 and try to border between 0.017 and 0.018.
For the 0.017 calculation, I got 1.09.
10 to the negative what? 5. Ooh. And so you got 10.9 times 10 to the negative 6. Well, that makes a difference because if it's 10.9 times 10 to the minus 6, we're too big. We need to go down. You double checked it, Jason? All right, then we'll go with that. 10.9 times 10 to the minus 6 is too big. Let's go down. Let's try just 0.016 and see what it comes out to, 0.016. Okay, now we went way too far, right? And so it's got to be a lot closer to 0.017. Do you guys see that? A lot closer. And so let's go with 0.017 what? Or no, 16, actually, 168? 8? Yeah. Oh, yeah. Okay. 8.47? 8.47 times 10 to the negative 6. Is that what other people got? All right. Still, okay, 8.5 to 10.5, let's say, and we want to go between those. Right in the middle, let's try to go, and slightly closer to this one. So maybe right in the middle or slightly closer would be 0.0164. How about a 0.0164? .39 times 10 to the minus 6. We're getting closer. Let's go with 0.0163. What is it? 9.15. Ooh, is that close enough? No. We wanted 9.14 or to round to 9.14, right? This is 9.15 what? 48? 9.154. And so it's got to be a little bit smaller. So 1.0162, no, I think 2 is going to be too small. So we'll go with 1.628. Let's just try 1.268, just a hair smaller. Right? 0.2 smaller. I mean, on the last digit.
Yeah,
9.1075. Too small, right? And so let's go 0.01629.
Nine
9.308. So close. So this is 9.15, this is 9.13, we want 9.14. So let's try 0.016295. It would probably be like 294 would have been a better guess because this is more than 5. That's all right. Just try it. $9.142 times 10 to the minus 4. All right. When do we stop? When do we stop? We stop like. It depends. We have two ways of knowing when to stop. One way is when the number of digits here will make no difference in the rounded answer here, right? And so we would stop at, let's say, 1, 2, 3, 4, 5, 6. Maybe at 6 decimal places, we'd probably stop. Right? Did we have 6 decimal places? Yeah. Or the other point where we stop is that this has got to round to k. And so this rounds to k, and so we'll stop here. Even though we hit 6 decimal places here, it doesn't round to k. We just kept going here. You know, some people will keep going and get this to 9.140, you know, but it's up to you.
Is it 10 to the negative 4 or 10 to the negative 6?
10 to the negative 6, sorry. So this is good. And so this is our x value based on the method of successive approximations. And so now let's go back.
Plug it in.
Yeah, well, you can go back and plug it in, and then what do? You check to make sure that the k value agrees, right? So we'll stop there. All right, any questions on this? Uh-huh. Because you want the percent change to to be less than 5%. You want the biggest percent change to be less than 5%. And so we calculate the biggest percent change and make sure it's less than 5%. That's why I picked that. Okay, any other questions? No. Do we have time? We get out what time? 12:35? All right. All right, I think we have time. So let's take a short break.